Alright, the final lesson for today has to do with Newton's second law. And we know that Newton's second law is the sum of forces equals the mass times the acceleration. Forces are the things that change. So this is the changer of linear motion. Mass resists change in linear motion. I should say change causer resists change. And the A is the actual change. Right, so another way to view this would be that the acceleration is equal to the sum of forces divided by the mass, where we're looking at this is our cause of changes in linear motion. This is how much the object resists changes in linear motion. So this is our actual change in linear motion. Now for rotational motion, it's just the analogs. So our analog for sum of forces would be sum of torque. Torque is the rotational equivalent of force. It causes changes in angular motion. And our analog for the mass, if you recall, if we look just across our table here, that's I, the moment of inertia. So rather than focus on the mass, we need to know how much mass there is, but also how far away is it from the axis of rotation. So we have I, that's a vector there, times alpha, which is the rotational equivalent of the acceleration. So I could just rewrite this as alpha equals the sum of the torque divided by the moment of inertia. And this is the change causer, this is the change resistor, and so this is the actual change in rotational motion. So we can use torque and moment of inertia to get a sense of what's going to happen to the object. So let's just do a quick example, because I think that's really about it, and I'll just box that up there so that that's another new equation for us. What you'll notice here is that we just have a lot of new equations in this unit, but they're all pretty much analogous to what we had in the past units in some way or another. So this is just the same equation, just for rotational motion. So let's just look at something. Let's assume that we have a long, thin rod of length L and mass m. So we have length L, mass m, and I'm going to apply a force. Let's say that it rotates about an end point here. Okay, so I'm going to apply a force maybe this way here, like so. I'll just go at the very end here. So I'll apply a force here. And in addition to this, if we assume that this is oriented horizontally and gravity pulls down, then we're also going to have a force of gravity downwards. And I'm just going to say here that the force of gravity is going to be equal to the opposite of this force of the push or pull. The reason why I'm doing this is because I'm going to highlight what this means for us in terms of what motion we get. So typically, in terms of if this was a freely moving object, right? If I apply a force here, I'm not going to actually get the object to rise or fall. I'll get part of it to rise and I'll get part of it to fall. But it's going to kind of stay in one place as long as I apply this force to it, because these two forces balance out, so it's not going to go up or down. But in reality, what's going to happen is if it's fixed at this point, what should occur is, because this force is acting at a greater lever arm than the force of gravity, is that this force should prevail. And we can also talk about the directions of these things. Okay, so the force of the push, if we think about what's going on with our lever arm here, so our lever arm comes out like this, right, all the way out there, so the entire length. If I look at this, if I kind of curl my hand in the direction that this would go, we might say that this force of the push is causing it to go counterclockwise, but for us that also means out of the screen. The force of gravity is trying to twist it the other way, so that means into the screen. And so when I go ahead and I do my sum of forces on this, well, if I do my sum of forces, I actually get 0, right? If I'm just looking at these things. there would also be a force from the hinge, but we're going to not worry about that too much right now. The reason that we're not going to worry about it is that if we're interested in the twisting motion of this, the force that the hinge exerts is exactly at the point of rotation, and so the R here is 0. That means that it can apply no torque. So if I do my sum of torques, so sum of torques equals I times alpha, I have two different forces applying torques. So I have R1 times the force of gravity, and I'll just make that in the negative direction, plus R2 times the force of the pull equals I times alpha. Now in this case, these two forces are the same size, so that makes things a little bit easier. And R1 is just going to be 1/2 of the length because it's acting at the center of mass. So I'm just going to call this negative 1/2 of the length times mg plus the full length times mg. And then over here I have my moment of inertia that I have to worry about, which, because it's a long thin rod about the endpoint, the moment of inertia is 1/3 ml squared. Right, if we look up there. So I have 1/3 ml squared times alpha. So you can see that we have a lot of common terms in this case, and so it's all going to work out fairly nicely for us. I can get rid of an m, that's in every term. I can get rid of one of the l's, because that's in every term. And then what I'm left with, if I look at what I've got over here, is I've got negative 1/2 g plus g, so this ends up being 1/2 times g equals, and over here I have 1/3 L times alpha. So if I just complete the problem then, and I solve for what the angular acceleration is in radians per second squared, I end up getting 3g divided by 2L. And so what this is telling us is that the angular acceleration is going to be bigger if I've got a bigger force, right? Because if g were larger, and this is the same size as this, then I would get a bigger force out, and that means a bigger torque, ultimately, and so we'd get more twisting to occur. But the longer this is, you can see that there's a little bit of balance occurring. The longer it is, the bigger my torques are, right? But the moment of inertia gets big faster than the torques do based on the length. And so the longer our rod is, the smaller the rotational motion change is going to be. So that's the basic idea with doing sum of torques. You're just doing I times alpha, and you can find the torques individually by taking the radius times the force. And that's about it. So hopefully that's fairly clear in terms of what's involved, and at this point you should be able to work on concept questions 1 and problem set 1, hopefully without too much difficulty.